All right, thank you for the introduction and thanks for having me. Now I brought you for the end of the day a bit of FPGA programming and a bit of my journey using the oneAPI I/O pipes for multi-FPGA communication. All right, so a bit about of the motivation. Maybe you saw this kind of figures here also on one of the posters. So this is my main use case, having shallow water applications on FPGAs, and this Bahamas mesh is one of our standard use cases. A bit of history. So the first of this FPGA designs we had was back from 2021. It was a single FPGA OpenCL design, and it was fast, but it stored all the mesh information on the block RAM memory, and though was limited to rather small mesh sizes. And after that, we started our SYCL, so first for the oneAPI implementation, which also runs on CPUs, GPUs, and FPGAs. And for the FPGA code path or part, we implemented array-specific caches so that we could have the feature of having as most as possible of the mesh locally on the chip. But when it's too large, the mesh, we can still run it, but then we have to load it from global memory. And maybe you also find this figure on one of the posters. And here you see exactly this behavior of the FPGA. So for the small meshes, it's quite fast. And then when larger portions of the FPGA, of the mesh comes from the global memory, which is sadly a bit slow on this FPGA, it gets a bit slower than the other architectures. Let's phrase it like this. So the overarching goal is also to have multi-FPGA support for the SYCL implementation. There was an open multi-FPGA design for this OpenCL version, which also performed quite nicely. But now we want to have this in our SYCL or oneAPI port, and therefore we wanted to explore a bit the functionality there, especially the oneAPI I/O pipes for direct FPGA to FPGA communication, and therefore as an intermediate step from a ping pong example to we have this simple Jacobi solver that is distributed about different FPGAs. So it's a bit more complex. We have 4 neighbors we have to communicate, so just an intermediate step. Okay, so a bit about the board. So in part 1, we have this Bitware 520N card. It has Stratix 10 FPGA on it. It's, I think, the most powerful version of this FPGAs. And the interesting part is now these 4 QSFP ports that allow to connect the FPGA, a single FPGA, to networking. And in the Noctua 2 FPGA partitions, we have 16 FPGA nodes with Intel FPGAs, and they are all connected to an optical switch. And we can configure this switch to connect one pair of ports directly with each other, so we can build whatever topology is possible there. Okay, switching to the software side, what do we need there? So this is the typical experience with FPGA programming. You somewhere hit a wall, and then you have to try to get it to find some solution, and you will find such an example later on. Okay, so this totally kills my animation, but I think you see what's highlighted. So first we have to define the structs. So there are here intentionally named after the port or the channel they are meant to, and output for the writing channels for a port, and input for the reading channels for a port. The idea corresponds with the port that they should target. So for the QSFP port, you have channel 0 for reading and 1 for writing, and so on and so forth. So in this example, this kernel output channel 0 should write on the first QSFP port, and this kernel input channel 1 should read from the first from the first QSFP port. Why that? I hope this will become clear in a second. Okay, then we define a data type we want to send over these channels. So these channels are 256-bit wide, and then we can send, for example, 8 floats in one row. Just a bit of template magic to not having to rewrite this all again. And then we use this kernel readable I/O pipe from the SYCL extension or the Intel FPGA extensions, and pass this struct with the ID in it to it, and give it the data type and also a channel def, which generates a bit of buffers next to it. So it's basically the number of reads. In this case, reads that can happen without a corresponding write. So it's a bit of buffering in between. And the same also for the writing part. Just that it's named kernel writable I/O pipe. Okay, so going to how this is used. Maybe I find another. It's better like this. Okay, so in Part and Bound, we also have this nice GUI to create links between the channels of an FPGA. So here in this case, I created links between the channel 0 of the FPGA 1 to the channel 1 of the FPGA 0. And if we now think this from the FPGA 0 point of view, we are first reading. So the other FPGA has to send a bit of data to us. Ideally, this happens in one clock cycle. Then we can do something with the data. And then we write it back on our channel 0. And of course, on the other side, the FPGA 1 has to receive that or read from that channel. Okay. So as I said, it doesn't work as expected. We observed that since oneAPI versions 23.2, this doesn't work with the mapping. So whenever I have only one read or one write and one write in the kernel, they all get mapped to channel 0. But as I said, I want to have it reading on the port 1 and writing to port 0, or the other way around. Somewhere this ID information gets lost in the synthesis process. I couldn't figure out where, but we figured out that somewhere in the synthesis process, this bc.xml file gets somewhere written. And here's the problem. This is the mangled name of the struct that I've created, but it should end up in a kernel input channel 1. And here it's in channel 0. But luckily, this file is not only written, but also used later in the synthesis process. So our solution on Noctua 2 is to have a wrapper for the system integrator, which is called right after this file is written. And this wrapper first fixes this bc.xml file. So for example, in this case, it would write here kernel input channel 1, so the write channel, and then proceeds with the normal system integrator. So after we got to this point, we could now have working direct FPGA to FPGA communication. So now getting to our actual application, the Jacobi solver. So we have for each FPGA, we want to use one MPI rank. Each FPGA can have up to 4 neighbors, and we decided for design having a compute kernel and extra I/O kernels. So one for sending and one for receiving. So in the end, we have 9 kernels running on the FPGA. And the I/O kernels only interact with the I/O pipes, and the compute kernel communicates with the I/O kernels via local pipes. And the compute loop is unrolled 16 times. So this is somehow the topology for here a 3x3 layout. So here we have compute kernels, and for each port we have a sending and a receive kernel. Note that the communication southwards always happens on port 1, while communication northwards always happens on port 0. The same is true for east and west communication. This allows us to have the same bit stream on FPGA, and with another with a large enough buffer size or channel depth. This allows deadlock-free communication, because then first every FPGA can write the stuff he wants to send and then reads, and it works. So having a deeper look into the implementation. So first of all, how does the data come from the compute kernel to the I/O kernel? So the sending size is here 8, because we have 256 bit and we are calculating in floats, so we can send 8 floats in one go. Then we calculate how many sends we need in each direction. Here I again take the maximum of the sending sizes, and I'm sending the values one by one from the compute kernel to the I/O kernel, just because it doesn't matter that much in that case. I could also set them in 8 chunks, because it has to happen somewhere, but I decided to have this not in the compute kernel. And I take here the maximum to have the sending in all directions scheduled to the same time. Then I have here this nice abstraction from the oneAPI samples, this unrolled loop thing that just unrolls this loop. And if we have a neighbor in that direction and we still have to send some valid data, we either send a validator or need head it if we are in the last chunk of data that is rounded to the next multiple of 8. And then we write it to a local pipe. So the local pipes are here organized in a pipe array, which is also a nice abstraction from the oneAPI samples, which is just templated and gives nice access to this read and write functions from local pipes, which basically works the same as the I/O pipes from a programming perspective. Okay, so now the data are sent from the compute kernel to the I/O kernel. Looking now at the send kernel. So they are instantiated for each port. So this channel ID goes from 0 to 3. And if we have a neighbor in this direction, we send in each time step for sends many times, as we have computed it before. Then we receive always 8 chunks from a local pipe and put it in one of the structs. And then we write it to the actual I/O port. So this write channel just wraps around this kernel readable I/O struct I've showed you in the dummy example before. All right, so that's the sending. Receiving works the other way around. There is no magic happening. And now getting a bit to the results. So in our experiments, we used oneAPI version 24.2.1 with the Quartus version 24.0, which is the latest one that is supported for our boards. And we are calculating in floats. The design achieved a clock frequency of 318 megahertz. It doesn't use that much of the resources, only a bit of the RAM blocks, which is due to the sending and receiving buffers. And since this is also a compile time constant, I chose the relatively large value to support large meshes. But still, the mesh is stored in global memory. Okay, first looking at the single FPGA performance. So you see here the updates per cycle per FPGA. So I told you that the compute loop is unrolled 16 times. So ideally, we could get there 16 updates per cycle per FPGA. But there are quite of effects here. One, this is not a totally perfect design, so we have a few unaligned loads in there, and then we at some point also hit the wall of the memory controller, which runs only at around 300 megahertz, which is a bit slower than our design and only provides around 70 gigabytes per second. In the beginning, we see here the overhead of a constant pipeline latency, but then it flattens out at around 10 updates per cycle on every FPGA. So I did the same experiment for 16 ranks. So this fluctuations for the larger mesh sizes is the same, so it seems to be somehow systematic. I wasn't able to really pinpoint it. The only thing I can say, there are mesh sizes that work a bit better than others. We believe that it's a combination of having the interleaving of the DDR channels and actual bank conflicts within the DDR banks itself, but we weren't able to isolate the effects. But yeah, for some mesh sizes, it works quite well. That's what I can say. Here's another weak scaling experiment. So again, on the y-axis, we have the updates per cycle per FPGA, and now for different rank counts and with a constant mesh size per FPGA of 2000 by 2000. And we see that overall it's relatively good weak scaling. It's rather constant. And the only thing that some here comes to an eye is that for when we have the n cross 1 layouts, something like this. So when we only have a north-south communication, then we are also just reading rows from global memory before sending and writing them back, which can happen a bit faster than reading columns from the global memory. So this might explain this bit of a difference for the layouts where we only have north-south communication. And as a last point, I have here the strong scaling experiment. So here I have a global mesh size of 3000 by 3000 for different FPGA counts, starting from 1 to up to 25. And if we are looking here at the 16 FPGA experiment, we see that we have a speed up of around 14.4. And for 25 FPGAs, we at least have a speed up of 70.2. And this is I guess, the typical strong scaling effect that at this point already the FPGAs are a bit underutilized. So here every FPGA has around 700 cross 700 elements per mesh. And this is the point in the weak scaling, or in the first plot, where it starts to drop it down. Okay, a bit about the conclusion. So it works to use the oneAPI I/O pipes for direct FPGA communication with our fix, at least in our cluster Nocta 2. With this templates that are also provided in the oneAPI samples, it allows us to have a quite compact formulation of this, and the scaling is also good. And for future work, I also already spoiled it. We want to implement this in our shell water code, and if you're interested in more of that, we have here also a poster, and Markus is also there. So if you're interested in our shell water design, and Markus already has designed for multi-device results for multi-device runs on the other architectures. So visit our poster if you're interested. And then thank you for the attention, and other questions.
Yeah, I have a question because I'm not really familiar with FPGA usage. Could you please explain what is advantage of FPGA, for example, compared to GPUs? Like, is it the price? Is it performance? Is it some presence of features?
So it's definitely not the price, and currently also not the performance, but basically the idea is that we could get a more application-specific data flow design. So idea in the beginning, the first OpenCL FPGA design were created because in this shallow water we have this unstructured and so random accesses, random memory accesses. And the hope was that this could be handled quite well for the FPGA because it has near memory and then it works quite good. Yeah, the idea is to have application-specific hardware tailored for the application, and there's the hope that it becomes quite fast.
So essentially performance, but it's maybe not always achievable.
Yeah, the idea is always that it works better than on standard solutions, but it's harder to achieve, I guess.
Okay, thank you.
So in this example, you said you basically just were memory bound then in the end. So it wouldn't have helped if you like replicated stuff and used like more of the resources on the FPGA because you already were memory bound, right?
Yeah, I will at least. So there are a few problems with the design itself. It's not fully optimized, but the memory is, so the maximum you get out of this memory controller is 70 gigabytes per second, and this is probably reached very quickly. So,
and that also means like the networking isn't much of a bottleneck then because it's already buffered well enough in the memory.
Yeah, the networking works quite well. So here I have the time per time step annotated, and maybe it's a bit small, but in this design we have each time step takes 0.14 milliseconds for a complete time step and a complete round of communication. So luckily communication is here not the problem.
But the communication always goes to the memory, right? So basically you are bottlenecked by the memory for the communication as well.
The communication is direct, but also more or less a bit stupid thing I'm doing in this design that I'm writing this results I received back to the global memory before actually using them.
Okay, so you could in theory directly read the received values into the compute kernel basically in theory. Okay, interesting.
So the idea was to explore a bit the communication capabilities and see that this works quite well. I didn't spend too much time on optimizing the compute kernels.
I would also like to add to the reasons why to use FPGAs. For once, you also have higher control how the data moves on the chip, which means you can build custom caches exactly how you need them for your application, which also means that the data moves less, and in the end also has the effect that you have a much better energy efficiency. Also, you can support arbitrary precision operations or bit-level operations that you just don't have on a CPU, like 96-bit popcode instructions are not an issue for FPGAs for CPUs and GPUs much more. And also you can do networking directly with the FPGAs. The very same devices that we use for computing are also sometimes used by networking researchers as smart links. And you can have also the control of the application on the FPGA so that the CPU basically just said, okay, here's the data, have fun, see you again in 10 hours. This is some of the advantages of FPGAs.